Hello, and thanks for coming to this webinar this evening. It's a beautiful evening here in Helsinki, Finland. So as everyone said, my name is Iisko Lappalainen. I run the product management here at Montavista Software. Today our topic is embedded Linux security infrastructure for automotive and IoT edge. So we're going to talk about a series of topics. We'll start with going through the motivation and increasing need for security. Why do we think that security is ever more important right now, and why should we be paying attention to that? Then we dig into shortly into the standards and certification, different categories of written requirements that both automotive and IoT cases can take advantage of. Finally, we dig into the actual topic of today, which is kind of technical solutions and an architecture suggestions that you can use to improve the security of your devices. Then Corey will talk about quickly an actual customer case study. He will go through detail about a specific case where we used SELinux, that is a mandatory access control framework that allows us to harden the systems for many different use cases. And then we have a small summary and closing chapter. First, going into the why more security now, we have the concept of I brand the triangle of threat: complexity, extensibility, and accessibility. So in principle, you can also only talk about complexity, and the idea here is that whatever solutions you put in place that increase one of these areas, you will, in a way, increase the exposed area of your device. So, of course, adding complex code will make it harder to be secured. The how much more extensible your framework is, the less likely that it can be completely intact as it comes to the glue layers between the different plugin frameworks, for example, and accessibility. So how much attack surface your systems have. Being accessible is one of the fundamental factors that increases the exposed area of your devices. Also playing in this is the sophistication of attackers, and this kind of a vicious circle, because we see that there's quite a bit of increased rewards in the scheme of cybersecurity. Based on the recent Atlas VPN research, for example, cybercrime is a $1.5 trillion market in 2020, and it's increasing with double-digit growth over a year. Then we also have aggressive release cycles, and some of the technology solutions we use are not that mature. That also brings in kind of the complexity triangle of threat aspect, as well as both of these play into the sophistication of attackers. Some of the specific areas where we drive complexity and openness, I mean, for the intelligent edge, the IoT devices, there's a lot of devices in there that were not meant to be connected, as in the accessibility factor, but now they're exposed to a different threat model that they were originally meant for. So this certainly increases the amount of security emphasis we need to have on this market. Autonomous driving, this is a massive technology leap for us in the automotive space. So going to this market will definitely make Linux more of a target of attacks, as we see already now in 2020. Specific malware that is targeting Linux is up 40%. So traditionally, what we believed as a Linux user, for example, on the desktop times, you don't need to have an antivirus software on your Linux box, for example, because there's no software and malware exploiting Linux vulnerabilities. But this is not correct anymore. So we have to take into account that Linux is one of the designs, one of the operating systems, which is in a way a target for the attackers as well. A lot of servers and IoT devices use Linux these days. Going to the specific topic area from a motivational aspect, there's a couple of recent breaches, and we review these recent breaches later in this presentation to see what we could have done to prevent this. The first is a supply chain attack from a known Solaris company. Should not mention the name of the company. It was a supply chain attack, and this allows basically using their remote management software to install updates onto the customers and end customers' targets that appear to be coming from a trusted source. This is one of the more tricky attacks to protect against with specific security facilities. But once we go through this at the end of the presentation here, we review something what could have been done. So there was a backdoor that was injected through a trusted update source into your device, and in this case coming from third party. The second attack is a script injection attack that also is a combination of an CVE exploit. So major retail chain was exploited, and their customer data was hijacked from the point of sales devices. But this was a complicated series of attacks. And here we should keep in mind that that attacks also have this chain of trust, chain of weakest link aspect. So an attack to be successful, it is must be successful in all its segments. So in here they had an initial breach through the vendors, in this case an HVAC vendor, where they managed to exploit a web UI which allowed them entry to the customer's network. And from there they used an existing vulnerability that allowed them to access a series of administrator accounts that were then used to go through different machines in the customer's network, and finally resulted in the ability to install the toolc drop here, the custom malware on the actual point of sales devices. Let's keep this in mind while we go through the sections in the presentation. When we talk about security safeguards, we typically talk about two different categories of them. The first one being reactive. This is things that you do for known intrusions or known breaches. The CVEs, common vulnerabilities and exposures, is by nature very reactive. So this is based on community maintained known problems of computer systems that are exposed on this the website maintained by MITRE. And there are different vendors who supply patches, and for your devices you will either have to supply it yourself or it comes from your operating system or software vendor, like a known entity as MontaVista, for example. We have auditing and logging that is primarily used to kind of figure out where you have attacks and how they have been taken into account. But basically, it's a very generic safeguard for you to know what's happening in the system. From a security aspect, it is mostly used for figuring out what is happening. But if you take that to the next level, you start going towards the more proactive area where you have intrusion detection systems, which besides logging and auditing, they also can act on the data, as in being a little bit proactive. That can also protect against this kind of unknown zero-day attacks. Finally, I put in here the over-the-air update scheme, and this is a protection facility that actually is more of a meta security setup here, since it allows you to basically patch holes from a security sense. That's what it's typically used for, so I consider it more reactive than proactive. But when we go into the proactive sense, this is walls that you build around your system. So the more of the nature of this is to harden the system against attacks that are largely unknown. The first one is system certification. So this is looking at the system from a very high level and matching the requirements against a known standard set of requirements. The second one, isolation and containment, is basically creation of domains with potentially different security facilities in them, so that when you breach one of the domains, you will not be able to go after the other. Root of trust and integrity management we cover in more detail in the presentation. And the idea here is that you create a trusted integrity environment, for example, trusted boot, to maintain different levels of trust within the system throughout the bootloader and the kernel, and going into the root file system itself. We have mandatory access control, SELinux, but Corey is not talk about in much more detail. And this is a very thoroughly capable framework for increasing the usage of Linux access control in the system. We have network security and deep packet inspection also. That is not really a target of today's webinar, but it allows hardening of the network channel itself, and also looking at the semantic information of the packages. Going forward to the standards and certification part, we have common criteria and EAL levels, which is a very well known, let's say, older security framework that is a specific process and a standardized approach to look at, let's say, defined security target, which is basically your device. You have to define what you want to protect against, and then you use the common criteria framework to make sure that you have the requirement means in place and the requirement infrastructure to create software and also hardware for this specific security problem. In my view, it's a very thorough and well-known framework that certainly can be used to harden your system on this level. The next here is the ISO 26262 and the related ASIL levels. It's more like more of an automotive safety environment where you protect against safety rather than security, but it also together, especially with some of the other standards, helps you harden the security framework because it contains a lot of infrastructure related capability of the company type requirements, and basically make sure that you can create secure software or safe software in your environment, widely used in the automotive space. And we have two kind of newer standards. US IT Cybersecurity Improvement Act is a new standard from US that allows you to allows secure development targets, and certainly it focuses on the safe updating of your devices, but it is also quite useful from a regulatory environment because it will mostly probably be extended throughout different types of designs besides the government area also. In here in the EU, we have automotive cybersecurity regulation, which is first of its kind in the automotive field, where they um, basically allow prevention of attacks, but also specifically the kind of monitoring and forensics capabilities to know when you have been attacked and what can you do. But it certainly has some prevention aspects in it. But these together are kind of enforcing more enforcement of ASIN standards coming from regulatory environment. Root of trust for the first of the kind of more technical components, we have kind of a trusted boot environment. What this does is that typically you harden the initial boot ROM of the system with the hardware key. So the initial root of trust in the system is often a tamper-proof secure key that is then used by sometimes in the ARM world, used by the trust zone executive, the sort of a virtual executive running in the trusted execution environment, which is own address space and the capability to have secure devices tied to it. On x86 world, we typically have the TPM that provides much of the similar functionality. So the tamper-proof secure storage is quite important for a hardware root of trust. And this is then used for your initial check of the boot firmware, and from there on you kind of have stage-wise attestation of different keys going through the boot stages. The next component, integrity management. In here we kind of extend what root of trust does for the base operating system, and we talk about the integrity management architecture IMA and extended verification module EVM for Linux, where we typically say this is integrity management. And what it basically does is allows certain files or your specific files or other files to be hardened against runtime tampering. So if those files were changed for whatever reason, the kernel will allow you to execute that or execute certain rules what to do in that case. So you will see when you execute binaries or read files that these are not the original files based on a digest that you store in the kernel memory space. You can combine this with the root of trust setup by attesting against in the earliest boot stage against keys that you store in the trusted execution environment or on your TPM. The default is using a hardware TPM on an external chip. Basically, this allows you to secure, encrypt the digests that are used to check the files. We can also accelerate this or offload this into separate devices using an example. We have a demo that we're specifically doing, and some cases below there where we accelerate the integrity management using facilities of the main chip in a secondary accelerator equipment. Here then we have an example putting this all together. A demonstration we did at ARM TechCon a few years ago. So the first stage is to boot the system in a secure environment, and then we have a secondary file system which is secured, and the key for that, decrypting that, is fetched from the trusted execution environment in this stage. So what we do here is that we boot first the initial boot ROM that is secured by the root key stored on the trusted storage, and then we extend that attestation chain throughout different stages. So the boot ROM attests the ARM trusted firmware, and finally the bootloader that actually loads Linux, U-boot, and U-boot will check the kernel and file system images and boot them. While the system is booted, it also uses this T-connector driver to connect to the secure OS side and fetch a key that is then used to decrypt a secure file system partition on the device. While this is a generic type demonstration, it allows different use cases. And for example, it allows you to have a tamper-proof secure memory partition where you can, for example, if your device is compromised, you have a large amount of memory that is accessible in that case, but the secure partition will not be available to the attacker unless it contains, unless he is able to retrieve the key from the trusted execution side. Finally, to talk about how do we maintain system integrity, we cover over-the-air update. And this is typically something that you do for supplying from securities and supplying patches to your fielded devices. Key criteria for this to work is the supply chain security that we talked about. It's really not a concept that the over-the-air update itself can provide for you, but it's more like a prerequisite for this to have any useful effect. Because if you don't have supply chain security, trusted updates will not work, as we saw on one of the attacks. So then you need, in addition, you need a robust build system that can, in a replicatable and secure way, create an update repository of images that you deploy onto the target. Then you have you need to have security for the update process itself, and this is both hardening the communication channel to the target, as well as authentication and validation of the updates themselves. Authentication being the most difficult problem in my view for the security environment. So there is certainly some attention that needs to be paid on this. And finally, you need the hardened on-target update facility so that you can reproducibly and reliably update the images on the target devices. Here we have a reference solution from MontaVista, just captured in a very high-level view, what we call secure OTA. And this allows the full chain of operation from creating the update images, delivering them into a secure repository, and delivering them from this repository onto the targets over an over-the-air connection or whatever connection you prefer to use. Then we have a reference flashing update setup that allows you to update the target device's firmware. The target update can be configured in different ways. Of course, the default is to use an AP partition update where you switch the active partition and you update always the other kind of, at every update you switch the firmware from one partition. Then you have a secure partition for fail-safe operation. From the image delivery, this is based on a standards-based setup. So we have paid a lot of attention and using known systems that are hardened and actually backed up by the NSA algorithms to make sure that your authentication and the security channel is intact. Then we of course have our own CGX product here as the reference, but basically it works on any Yocto environment to deliver an update into the repository and have that as part of the manifest and available to different types of user equipment on the field. So each of the equipment or the devices on the field will be able to retrieve the right images for itself through this kind of end-to-end authenticated setup. With this, I'll give it over to Corey for going through the SCLinux use case.
Um, as Isco has already discussed, the days are gone when you can ignore security in embedded devices. It's just everything's in the internet now, everything's connected. It's just not a situation where you can ignore it anymore. If you're not using best practices, someday you will probably face litigation based upon that, just like the automotive industry did when they first started using software in cars. So I'm going to be talking about SELinux. SELinux is not a replacement for all the things that Isco talked about. It's more of a supplement. You still have to have timely updates on your software. You still need to do root of trust boots and secure boots. SELinux instead provides a level of protection for containing an intrusion. So it is a centralized security model. I used to think that mandatory meant it was you had to specify everything, which is true on SELinux, but mandatory actually means centralized. It comes from the security world as opposed to the software world, and so they have a little bit different terminology. When you get into SELinux, you discover they'll use words for things that don't make sense from a software point of view, but make sense from a security point of view. So mandatory means centralized. There's one security model for the entire system, and it's denied by default, as I said. So everything that has to be done, or that a program piece of software has to do on the system, has to be allowed. It's not like you deny it things, you have to allow everything. And as I said, it's not so much preventing the intrusion, it's containing an intrusion when one happens. So we just went through an exercise with a customer where we put SELinux onto a deeply embedded system. It was running off RAM disk. It had a lot of things that were very different than a standard system. We thought, we had done reference policy things before in SELinux and provided that for customers. But we discovered very quickly this sort of system in something like an IoT type system, the standard reference policy in SCLinux is just not suitable. It's too large, it takes too long to load. Since it was a RAM disk, we couldn't start with all the different files with their proper security labels on them. So we had to apply that at runtime, and on the standard model, it took like 40 seconds. So we were in a bit of a bind there, figuring out what we were going to do. Fortunately, the person I was working with was talking with some people that are security experts, and they mentioned that the OpenWRT group was creating a viable policy for this, and it was a wonderful thing because it was almost exactly what we needed. So next slide, please. So as I mentioned, should you use SELinux? You probably should be at least looking at doing it. And SELinux has a reputation for being difficult. There is a learning curve, I will say that. It requires a lot of detailed knowledge, but that has a lot of positive effects too. I'll talk about that in a second. OpenWRT policy makes things a lot easier. It was a vast improvement. It makes it at a point where it's not terribly hard to use anymore. It's actually pretty easy to use once you learn how everything works. It's using a new language. The old language was a very raw language. It used M4 macros. It was very difficult to use. And the new language is much, much easier. It allows you to create macros easily and refer to other things and reuse things in an object-oriented sort of fashion that makes it much simpler. That said, you still will need expertise in SELinux. You can't get away from that. One thing that I discovered in doing this exercise and working with a customer is that it actually helps you think about the design in a manner that's more secure. So actually, the customer had actually done a very good fundamental design on how they designed their system, but they had made some mistakes in their software. And for instance, they had executable stack, and SELinux found that for us. They had been forgetting to close some file descriptors before they passed them on to other programs. SELinux, of course, found that because it's going to say, hey, this other program doesn't have the permission to access these things. So it helps you think about how you should design your system, and it helps you find problems in your system that would have otherwise probably gone unnoticed, that could have been attack vectors. And so it's a very good thing. This was a new learning for me in going through this exercise. It's a very good thing for that sort of design exercise. And another big thing that SELinux provides is audit logs. So if somebody has compromised your system and is trying to do things that are not allowed by that piece of software, you'll get logs. You can catch those logs. You can detect when your system has been compromised probably much more quickly than any other mechanism that you will be able to use. So let's actually just jump to the next slide. So this is just a little exercise or a little thing to show how SELinux works and how you might design your system for best security. So SELinux has these things called contexts, and a piece of software runs in a context, and every object in the system has a context, and contexts are permitted to access other contexts. So for instance, in this application, you might have SELinux running or your network access that's doing all the parsing and all those sorts of nasty things that are security problems. And you might run that in a context that is very limited. All it can do is network access and pass messages off to some applications. That is the most likely place you will get an exploit, because you're likely going to have a buffer overflow. You're going to have something like that was missed in all the parsing code. But if that's limited in what it can do by SELinux, then that compromise is really not going to accomplish very much for an attacker, and you will detect it and figure it out. So you can limit it there, and then the applications themselves can run in SELinux contexts. And then if you have any sort of high security type of thing, key access, key processing, database storage, put it in its own context, or for keys, you probably want to put them in a TPM, but you can move those things into their own context, so even the applications can't see them. They have to go through some sort of API. So although it doesn't make the attack of a system impossible, it makes it vastly more difficult than it would have been otherwise. And this also shows the kind of good design that you would want to use in your system. So you want to divide your system up into pieces that are contained, where the security of them can be contained, like this. And you want to think about your system from a design point of view, or your system designed from a security point of view to be able to do this. And that's going to provide the best security possible for your system. If your application is just one big program and it does everything, SELinux is not going to do very much for you, because that program has to be permitted to do everything. If somebody compromises it, then they can do whatever that program can do. Whereas if you design your system in a more secure manner like this, it makes it much harder for an attacker to get into your system and do anything bad. So I mentioned this because it starts, you need to think about it from a design point of view, and from the beginning if possible. And I will mention that it does take some skill to do this sort of thing. It takes some skill to use SELinux. you will probably need help to get started. Once you get started, you probably wouldn't need help after that. Once you have expertise gained in your organization. But getting that expertise will take some time. Having somebody help you, like MontaVista, will speed things up a lot. And it has for the customer that we're working with, and it will move you a long way towards best practices and avoiding the trouble that comes with getting your systems hacked, your systems being used for other things, all the issues for that sort of thing. It will help immensely with preventing that sort of thing. Obviously there's nothing perfect. There is no perfect security, but if you waited for everything to be perfect, you would never be able to accomplish anything. Instead, this provides best in class type of security to implement all these things together with SELinux as part of it. So with that, I'll turn it back to Isco. We have a lot of questions.
Re-enable my video also. Please go to the next slide, Evelyn. So just for a final slide before we wrap up, we could take a quick review of the exploits we covered in the beginning. The first was this supply chain attack, where the malicious updates were coming from a trusted source. So the idea was that the hack itself was in the very early phase in the supply chain. So the update itself was malicious, though considered secure. So what we could have done here is that obviously we have to have a hardened update process, which is kind of a taken here. I mean, the supply chain attack is somewhat of let's say a semi-security exploit or meta security exploit. So it's hard to protect against. However, with SCLinux and the different facilities Corey mentioned just briefly just a moment ago, we would be able to mitigate the effect. So that's also one difference between the so-called reactive facilities and the proactive security walls that you build around different domains, for example. So in this case, if you had this backdoor in here in your system injected by the supply chain attack, you could have certainly mitigated the damage by having SELinux and looking after the packet sent by it, for example. You could have mitigated the damage by having domain isolation. Like, for example, this program is not allowed to open ports. Only in this domain you're allowed to access the network. Or IDS, intrusion detection, could have noticed this as well. The second, where the retail chain was attacked through this multi-stage attack through the HVAC system, you could have protected against different steps of the attacks with different measures. The first one, through the HVAC system's initial injection point through the web script, you could have protected with SELinux again. So if the web application is only able to do certain things, it will not be able to go after different files that it's not supposed to, or listen to the network, for example. Integrity management could have solved that in some cases. The hash duplication attack, kind of exploiting a known vulnerability, is a CV that you should have patched. However, you could have had domain isolation IDS, like not all systems would be able to access all systems or others. Or you could have had IDS to notice the traffic that is going on the line that is malicious. And finally, you could have prevented the attack, because all attacks are also, like the same as the security, it's only as strong as its weakest link. That is the same for attacks also. So this attack would have yielded nothing if the final bit here would have been prevented. For example, you would not have been able to gather the information about the users and their credit card information via the custom malware if you would have, for example, SCLinux or integrity management in place. So you would not have been able to install this custom malware onto the point of sales devices. Domain isolation would have been solved in a different way, but all of these facilities would have been would have been good to have on the devices and configured correctly. Also, like Corey mentioned about SELinux, not just having it, you have to configure it properly. With that, let's go to the closing slide. I think we're a little bit short on time also. Just to summarize quickly what we've gone through here, we went through the increasing rewards that there are for attackers to exploit devices. We went through what are the different areas driving complexity and accessibility and extensibility in the world for edge and automotive devices. We went through some standards, like a very high level concept of security, looking at standardized requirements, forcing a security model. But finally, we looked at specific solutions that you can implement today in your system and harden them against these zero-day exploits or react against known exploits today. Then we briefly talked about over-the-air updates and how important that is in maintaining the system integrity. So we here at MonteVista are certainly available to help. If you need us in your projects, feel free to contact us.